Thank you everyone for inviting us in this webinar. This work is between Giorgos Kouroupetroglou, myself, Spiros Polychronopoulos, and Kostas Pakogiannis. I'm a music composer and an acoustician, and I'm working in this project about 2 years now, since the beginning, in the Department of Informatics and Telecommunications in the University of Athens. What am I going to talk about? I'm going to talk about this project. It's called MNESIAS, and I'm going to highlight in the introduction the motivation and goals. I will explain briefly a few techniques that we used in order to sonify the musical instruments, and I'm going to show you a few results and the applications in the end that they are aiming for scientists and museum visitors. So our motivation is we have lots of excavated instruments here in Greece, lots of museum exhibitions, lots of published studies, new information, findings and discoveries, and the development the last years of archaeomusicology. All these are based in the visual stimuli. We are aiming to go forward for what the instrument is really was built for, which is the auditory effect, and this is lacking for museums. So the visitor of a museum cannot hear the sound of the instrument, and the visitor cannot interact with the instrument, not even with an application, in order to get an audible stimuli from the instrument. This is our main focus though. So the main targets of this project is obviously to accurately simulate and sonify the ancient Greek musical instruments, develop a user-friendly digital tool that would be an application for the museums and the musicologists, the scientists of the museums as well. And lastly, we are going to evaluate the applications in the real environment, which is a museum. As I said, the applications as all this work is targeting to scientists and museum visitors. Two different approaches there. So regarding the sound reconstitution of an instrument, you have one way. You can go for a replica or a digital instrument. They both have pros and cons. For example, the replica has obviously better physical interaction. You actually interact with the instrument itself, haptic experience, and it's obviously more visually pleasing when you put it in the museum. Rather than a digital instrument, you have more flexibility varying the parameters of the instrument, and that's rather important when it comes to research methods and research tools, as well as the interaction of the instrument through an application in the museum. So you can vary few geometrical, for example, parameters. For example, for aulos, you can change the length of the bore or any other parameter and get the audible stimuli. Obviously, now we have to take that into account as well. It's COVID safe. You don't touch, you don't breathe inside tubes, you don't blow inside tubes. You just play with an application. Building time is not with us, even if it's for replica and a digital instrument. It takes a lot of time to build a digital instrument and a replica as well. Building costs obviously is less for a digital musical instrument, and it's also multi-user in digital instrument. Lots of users can play with the same application. Here I'm showing you a few pictures about what's happening in our lab. We're making the instruments, we're making the replicas. This is from a previous grant, a previous work that has been done, and we still have the equipment to work with in this project as well. And we keep making replicas in this lab. So the digital sound synthesis techniques, we have sampling and spectral modeling. They both have prerequisite that an instrument needs to be in place. So you need to have a recording. Sampling, you need to have a recording for the sample to record the sample and play it back. This is the technique of sampling, and the technique of spectral modeling. You need to have a recording from an instrument from the real instrument or a replica in order to be able to generate the sound using the frequency, trying to match the frequency response of the instruments. So both techniques need sound recording, and this is not the way forward in our case, which we are talking about ancient musical instruments, where you don't always have the instrument intact or a replica. So physical modeling technique, you just describe the geometrical parameters, the materials, and so forth, the physics of the instrument in order to get the sound. So imagine you have an instrument that you have found part A, part B, but the part in between, in the middle, is missing. You can easily do that using physical modeling and just assume a part in the middle and play a little bit with its parameters. So it's a one way forward for, in our case, physical modeling. So with the instruments, what we have used in this project, we have used the digital waveguides, simulating the air particles resonations. And imagine you have a physical instrument here, the embouchure, the bore and the bell. We simulated the embouchure as a digital filter, the bore as a two-ways digital waveguide, and the bell as a digital filter as well that simulates the effect of the bell. So it was a three-part simulation. So here I'm going to play a few samples from the instruments that you see here. We randomly chose these geometrical features, but you can obviously, with our application, change these features, these parameters. This was aulos. This is plaielos, salpings, and this was sittings. I hope the sound was okay. So string instruments, we used a completely different technique, not completely different, but different in the part. So we simulated the instruments in as a two-system instrument. The first system is the string vibrating, and we did that by means of digital waveguides, and that was a DSP method commonly used for string vibration. And then the body, which is a lot more complex movement due to the geometry and the material as well, we used finite elements method. So the body vibration, we took an impulse response on the bridge of the instrument. Here you see the animated figure here of a formings as the body is vibrating through the bridge. The bridge is vibrating and transmitting the vibration to the rest of the instruments. This is simulated using finite elements method, and those two systems are combined, coupled, and we get the auditory result after that. So audible result after that, sorry. So first, formings. This is the sound of formings with the simulation technique. This is helis, trigonon, parvitus, and kitharis. So few results here. Sort of innovation that we have already published a year ago in IEEE journal. So previously, the physics and geometry using physical modeling based methods was taken into account in order to predict the instrument's musical scale. We introduced something new that was never introduced. That's the player's interaction with the instrument. And the player's interaction with the instrument is quite significant when it comes to musical scale, because the musician, as the musician is playing the instrument, tunes the instrument quite a lot, especially in wind instrument of aulos, for example, which you have a double reed. the player's interaction is quite significant because the player can bite the reed a little bit more, and it changes the output or signal significantly. We simulated the player's interaction as the minimization of partials or overlap, going towards a greater harmonicity there, and this is coded as a spectrum's entropy minimization. That's why the paper was called EndroTuner. So our results compared to previous methods for Avlos of Louvre, we have here in our work, we have more consonant intervals, 56 in total, and not only more consonant intervals, but also better absolute deviation as well, as we see more than 62% are from 0 to 5 cents here. So another technique that we used in order to enhance the synthesized sound accuracy is that we used analysis by synthesis. This method is maximizing the similarity between the synthesized sound from the physical model and the generated signal from the replicas of the ancient musical instruments. So here in this technique, we need basically a replica in order to reproduce a sound, and we are trying to match this sound with the sound that is our model is generating. We did that giving, for example, the building parameters of the physical model, the geometry and material. So the physical model is outputting a synthesized signal. Then this signal is being compared with the recorded signal from a replica, or even better, a real instrument, a real ancient instrument. And then this is degree of simulation of similarity is being calculated, and then this is fed to analysis by synthesis, which is then outputting a correction factor set to be applied to the physical model. This loop goes on and on for a few iterations there, and then after the iterations, after lots of iterations, then we get an output, which is the optimal correction factor set, and then we apply this optimal correction factor set to our final physical model. And these are the results of this technique. Here on the top, you see this is the frequency response of the physical model and the recording. So you see a little bit of mismatch here in the fundamental frequency as well as in the harmonics. Whereas when we used the analysis by synthesis technique as well, here we have better results. So the results are matching the recorded signal, which is the ideal signal. As I said, this is mainly, the applications are mainly focusing for scientists as a strong research tool, which you can amend and change all the parameters of the model, and you get sonification, and you get more musicological information as well for musical scale and intervals, as well as it's a strong tool to get more engagement from the museum's visitors. They have something to play with, to interact with. They go for an augmented reality. We are designing augmented reality applications that will give more engagement for the visitors, educational plugins, and so forth. So also in the final step, we haven't done that yet, but it's in it's going to start in next couple of months. We are going for the user's evaluation, and this is mainly human-computer interaction techniques, which is usability and user experience techniques, and also obviously measurements, which is objective and subjective, such as eye tracking and questionnaires, respectively. And also I want to highlight here that we took into account the latest ISOs for accessibility as well. Here I'm just showing you a screenshot from the application. We have lots more features here, but that's an old one, and basically that's the user is changing the variables, and you see it visually. You press play and you hear the instrument, and you close and open the tone holes and you hear the results. The consortium, lastly, is ourselves, which is the Speech and Accessibility Laboratory in the National University of Athens, 2 museums, and a company that is called the Adrasis, and it's responsible for the software development and the application development of the application. Thank you very much for your attention.